Okay, YouTube, in this video we're going to look at one of my favorite factoring patterns that we refer to as a difference of squares factoring pattern. So this is one of a special set of factoring patterns, and we're going to start by considering multiplying these two sets of binomials. So the first thing I want everybody to notice is this: we have x plus 3 times x minus 3, and over here we have 2x plus 5 times 2x minus 5. I think the idea is that we're almost squaring these binomials because they're almost identical. It's just that one is plus and the other one's negative. So if I were to actually FOIL this out, we'd say first we would get x times itself, so x squared, and then we'd get minus 3x plus 3x, and then finally we would get something times itself, but one's positive and the other one's negative, so always negative in the back here, and then we would say 3 times itself, which is 9. So what we notice is that these middle two terms in our FOIL, the o and the I, cancel out. And we end up with this: we get x squared minus 9. So now looking at this other one, we'd say, okay, well, what would we get? We would take 2x times itself. These are nearly identical, so we would say we get 4 and then x squared. Then we get 2x times negative 5, which is negative 10x, but then we turn right around and we do the same multiplication, but we get a positive 10x. So I'm just going to go ahead and say this now. We get another cancellation in the middle, and then we get 5 times itself, but one's positive and the other one's negative. So this also is a negative thing, and we get negative 5 squared in the back. So really simplifying this, we get 4x squared minus 25. So what I want to point out is this, or actually ask, is these questions. We say, what is true about the values we get in our product? So I say, what's true about these values that you see here? I mean, what's so special about x squared or 9 or 4x squared or 25? And I hope you're realizing these are perfect squares. Like 9's a perfect square of 3, 5's a perfect square of 5, 4 is a perfect square of 2, and x squared, as a matter of fact, is a perfect square of x. So my next question is, what is true about the middle terms when we multiply these out? Well, what happens is these middle terms, as a consequence, always cancel out if the two things you're multiplying look almost identical, but one's positive and the other one's negative. So this special factoring pattern occurs this way. We say, well, that's foiling it out. We want to go backwards. Could we think of the two things that we multiply out to get this right here? And if you ever have what we call a difference of two squares, I refer to this as dots, D-O-T-S, difference of two squares. We would say that, well, then you really have a difference, which really just means you're subtracting two things that are perfect squares of a number. And what you always get is a plus b times a minus b, where these are identical. And a would just be the square root of this first value here. So if I said, well, what could I take times itself to get 4x squared? Really the square root of 4x squared. We would get 2x and 2x. That would go in the front. And then this b part, the b part is really what I could take times itself to get this second perfect square, which in this case, say 25 would be 5 and 5, and then we would just put plus in one and then minus in the other one. These are really actually fun to do. So we say in a factored expression, we say, or in the factored expressions, we say the factors a plus b and a minus b, they have names, and they're referred to as conjugates. Anytime in math you have two binomials where they're identical, but one is positive and the other one is negative, we refer to these as conjugates. So that'll be important in the future. So what I want to do is, looking at all these down here, factor these following expressions completely. And in each instance here, it looks like we have squares. So x squared and 36. So if this is going to factor, then it would factor into this. And we would say, well, what could I take times itself to get x squared? Well, it would be x and x. And what could we take times itself to get 36? Would be 6 and 6, and then we would just make one of these positive and the other one negative. This would be really easy to check. We would get x times x, which gives us this x squared. And then in the last part, we would get a negative 36. That gives us a difference of two things. And then negative 6x and positive 6x would cancel out. So looking at this, we say 9x squared minus 1. I put this one on here because a lot of people tend to misread this, or not misread it, but they forget that 1 is a perfect square of 1. So this is a difference of two things that are perfect squares, and so we would get 3x and 3x in the front because 3x times itself gives us 9x squared, and then 1 and 1 in the back because 1 times itself would give us 1 there. We'll just make one positive, one negative. And again, let's check. We get 3x times itself, there's that term, and then positive 1 times negative 1, there's that term, and we would say that this negative 3x on the outer and then positive 3x on the inner would cancel out. So now this last one. The interesting thing is, I want to point this out here. This is not a difference of two squares. This is a sum of two squares. And what I would encourage you to do is try to factor this one. My question is, would it factor out into, I guess it'd be 2x and 2x, because 2x squared is 4x squared. And then we say, what could I square to get 5 or 25? It'd be 5 and 5. Does this factor? Like if I put a plus and a minus here. And what I want you to see is, if we check our work, we would certainly get the 4x squared. That totally works. and we get a negative 25 in the back. And the middle terms would cancel out. As a matter of fact, this is not the same thing as what you started with. So I tell people, play around with this. Could we change our factors so that we get 4x squared plus 25? And what I want you to see is the moment you change this to a plus, maybe that's it. You get the 4x squared, and you get the 25 part, and it suddenly becomes a positive 25 in this case for your f and your L. But checking your O and your I, look what you get. You get a 10x and a 10x, which is actually plus a 20x. And that's not the same thing we started with. And even trying the other way, 2x minus 5 times 2x minus 5, we would still get 4x squared in the front. We would get a positive 25 in the last spot, positive, that's good. But then we would get negative 10x and negative 10x, which is negative 20x's. And so this is also not the same thing as the original. So what you would write here is this is prime or not factorable. So just know that a difference of squares factors into conjugates, and a sum of two squares cannot be factored. Cheers.